Today we're cutting through the hype and going straight to brass tacks, unsupervised anomaly detection with a plain vanilla autoencoder. We'll prove the concept on the classic iris dataset, small, clean, and perfectly balanced, before you swap in your vibration, pressure, or network traffic feeds. The mission is simple: train only on healthy data, set a hard statistical threshold, and flag everything that doesn't belong. You'll see every step: dependency install, data wrangling, feature scaling, network design, threshold calibration, and an honest evaluation. Along the way I'll call out the industrial gotchas you'll face when sensors drift, distributions shift, and false alarm budgets get political. No black box magic, no slide deck fluff, just executable code and the critical thinking behind it. By the end, you'll have a deploy-ready template you can port to any factory floor or edge gateway in under an hour. Let's get to work. We open with the bare essentials: no kitchen sink. Scikit-learn, the workhorse for classical ML and the official home of the iris dataset. TensorFlow gives us Keras, the high-level API to stitch layers together in minutes. Matplotlib, still the fastest way to get a quick sanity check plot. Pandas, 90% of the time you're wrangling CSVs, Pandas makes it bearable. The quiet flag stops pip from spewing pages of build logs, important for clean notebooks and automated CI runs. Total install footprint, well under 1 GB, so even a modest collab instance handles it. Next, imports. This is where most notebooks get messy, ours stays surgical. NumPy sets the numerical backbone. Every tensor eventually boils down to a NumPy array. Pandas for data frame operations, SQL-like querying without the SQL Server overhead. Matplotlib.pyplot, default plotting. In production you'd export JSON to Grafana, but here a quick histogram suffices. From Scikit-learn we bring in load_iris, the dataset loader. Standard scaler, forces mean equals 0, std equals 1, this prevents one feature from swamping the gradient. Confusion_matrix, classification_report, rock solid, no dependencies on TensorFlow's flaky metrics. Finally, layers, models from TensorFlow.Keras, the modern wrapper that hides TensorFlow boilerplate. If an import fails here, stop, don't code around a broken foundation. Here's the data pulse of the demo. We call load_iris, as_frame equals true. That as_frame parameter quietly saves hours, you get a pandas data frame instead of a raw NumPy blob. We manually set the column names because iris still ships with archaic spaced headers. Species counts come back 50/50/50, that balance is gold for teaching but unrealistic in production, where anomalies are less than 1%. Industrial tip: always log your class distribution. If the ops team later asks why recall cratered, you point at the imbalance, not the model. This single line, df, anomaly, equals, df, target, equals 0, turns a 3-class problem into binary health monitoring. In plant monitoring you rarely have labeled failure modes, you know what good looks like, and everything else is suspect. We convert the boolean to int for compatibility with scikit-learn metrics that choke on bool. Result: 50 zeros, healthy, and 100 ones, toxic. Quick check with np.binCount confirms the conversion. Reality check: if your anomalies outnumber normals in the wild, you mislabeled something. Stop and audit. Unscaled data ruins neural nets. Petal width sits near 0.1 cm, sepal length near 7 cm, gradient descent will chase the larger numbers and ignore the rest. Standard scaler shifts every dimension to mean 0, unit variance, classic z-score. Could we use min-max scaling? Sure, but z-score preserves outlier distance better, which matters for reconstruction error methods. Rule of thumb: scale using parameters learned only on training data. Here we call fit_transform on all samples because iris is toy size, in production use a pipeline that fits on healthy data only. Architecture time. Input layer, 4 neurons, 1 per feature. Encoder, compressed to 2 neurons, then down to 1, the bottleneck. If the network can distill a healthy iris into a single latent variable, anomalies should explode when forced through the same funnel. Decoder, mirror backup, 1 2 4. Symmetry keeps parameter count low and forces information to compress. Activation, ReLU everywhere except the final layer, raw linear so we can reproduce negative scaled values. Total parameters, 29, tiny, but enough capacity for 4 features. Compiled with Atom and MSE loss, Atom is basically the industry default unless you have non-stationary data streams. We run 50 epochs, overkill for 50 samples, but it ensures convergence. Batch size 16 keeps gradients noisy enough to escape shallow minima. Validation split of 0.2 means 10 randomly held out normals per epoch, giving a sanity check for overfitting. In this micro demo you'll see loss plateau quickly. Notice the loss falls from almost equals 1.2 to almost equals 0.88. On unscaled data that number would be meaningless, on z-scores it actually tracks variance reconstruction. In a real plant you'd enable TensorBoard, watch for divergence, and set early stopping thresholds tied to MTBF goals. Post-training, we compute reconstruction error for every training sample, basically asking, how bad does the network mess up when everything is healthy? We summarize that distribution with mean and standard deviation, then define a threshold at mu plus 3 sigma. Statistically, in a perfect Gaussian world, that captures 99.7% of the healthy population and leaves 0.3% allowed false alarms. Here, the magic number is 2.5335. Industrial caveat, sensor noise is seldom Gaussian. In production, you might fit a KDE to the error curve. Use the 95th percentile instead of 3 sigma. Dynamically adapt the threshold over a rolling 24-hour window. Testing time. The confusion matrix tells the cold truth. True normals, TN49, only 1 healthy sample flagged, acceptable. False positives, FP1, engineers can live with an occasional extra inspection. True anomalies, TP7, that's recall is almost equal to 7%. Low, but remember versicolor and virginica aren't wildly different in raw feature space. False negatives, FN93, misses. In a safety-critical system you tune the threshold lower or redesign the latent space. Precision on anomalies sits near 88%, when we do raise the alarm, it's usually right. The histogram drives the point home visually. Setosa errors cluster tightly near 0, the other species are broader, but overlap significantly. That lone high-error Setosa might be mislabeled or genuinely odd, worth investigating. In practice, you'd iterate, widen the bottleneck, add nonlinearities, or even switch to a variational autoencoder. But the workflow, train on healthy, compute threshold, inspect confusion matrix, remains the backbone of industrial anomaly detection. We've walked end-to-end through an unsupervised anomaly detection pipeline, data ingestion, scaling, training a lightweight autoencoder, threshold calculation, and honest evaluation. Swap iris for vibration data, network telemetry, or PLC sensor streams, retrain, and push the model to your edge gateway or SCADA server. Remember, the quality of normal data and the discipline of your threshold calibration determine success more than fancy architectures. That's the straight answer, no fluff.